Good morning, my friends. I just want to go over with you. This is very short, sweet, and to the point, so hopefully it's mostly review for you guys. But I never want to just assume too much, and it's always a good review. So we're going to start our unit about matter. And to start the unit, we're going to take a look at elements, mixtures, and compounds just really quick. So first off, I want to take a look at, of course, we got like Grumpy Cat here. Once I told a chemistry joke, there was no reaction. Just wait to hear all my jokes. Just wait, for real. Anyway, mixtures, elements, and compounds. Of course, scientists like to classify things because that's just the way that we work. And one way is we go by its composition, and composition is basically like structure. So you hear me say structure and function often. So this is mainly the structure here. Ultimately, all matter can be classified as mixtures, elements, and compounds. Please understand, everything on this universe, in the universe, can be classified as matter or energy. And all matter can then be classified further into elements, mixtures, and compounds. So why isn't it a good idea to classify it just by solid, liquid, gas? Just because we know one substance can exist in more than one phase. And actually most substances can exist in more than one phase. And it's usually pretty much a simple phase change based on the energy that's gained or lost. Why isn't matter classified according to its physical characteristics, such as color? So obviously, the structure, so color is great, but it really doesn't come up with the composition or structure. Sorry, I kind of clicked that away pretty quick. So obvious, it's kind of obvious looking at these three designs here. But scientists do ask themselves these questions, and these are the three most important questions to ask when you are deciding if something is an element, mixture, or compound. And then furthermore, describing what kind of mixture it is, for example. First off, is the matter uniform throughout? Does it look the same throughout, or can you see distinctive differences? Second question, can it be separated by physical means? So, for example, can you literally pull something apart? Can you boil some water off the top? Can you filter something? And then finally, can it be separated by chemical means? And separation by chemical means, that means that you have to actually add another chemical to have a chemical reaction to pull something out. So when you ask these questions, scientists, they can classify matter then into mixtures. And mixtures is probably the one thing that we use, honestly, the most in chemistry. And so these are two or more substances that are not chemically combined with each other, and they can be separated by physical means. So when the substance is in the mixture, they still retain their individual properties. It's not it's kind of like, for example, a relationship. So if you have one partner and a second partner, and each partner has individual interesting characteristics, and they are in the relationship, each partner still has their individual interesting characteristics, but then you also have characteristics together as a couple. So it's kind of the same concept with mixtures. The reason why we use mixtures so much in chemistry is because solutions are mixtures, and we make solutions all the time by dissolving things into water, especially water. It's possible to have others, but we typically use water because it's our universal solvent. Elements are the simplest form of a pure substance. They cannot be broken down into anything else by physical or chemical means. So if you have copper, then you can only break that copper down into copper atoms. You cannot break it any further to form something else. So even if you break down a copper atom, you can only have copper protons or neutrons or electrons that also describe copper. Compounds are pure substances. Notice I said pure substances for elements and for compounds. Pure substances that are the unions of two or more elements. They can be broken into simpler substances by chemical means. So remember, that's like adding something else to a substance to pull something away. So you have to actually have a chemical reaction. And I'll show you some examples of that in the lab. So this is just a little flow chart, and it's kind of nice to kind of think about real quick. Not by any means do you need to like necessarily write this down, but it's just something to like kind of go through in our head. First off, you look at the matter and you think if it's uniform throughout. And if it doesn't look the same throughout, then it's a heterogeneous mixture. And if it looks the same throughout, then it's homogeneous. But homogeneous can mean more than one thing. Heterogeneous and homogeneous, the difference between the two, just use the prefixes. Just like a heterosexual couple is a man and a woman, and a homosexual couple is a same-sex couple. It's the same. Homo means same. Hetero means different. Okay? Don't make that harder than what it needs to be. Homogeneous, if it is homogeneous, can it be separated by physical means? And if that's true, then it's a homogeneous mixture. So we know it's a mixture, it's a solution. If it cannot be separated by physical means, we know it's a pure substance. And that pure substance is either going to be an element or a compound, because we want to see, is it just one type of pure substance, or is it like a multiple elements of pure substances? So with it being uniform throughout, heterogeneous, it's considered the least mixed. It does not appear to be the same throughout. Particles are large enough to be seen and to be separated from the mixture. Say, for example, you have granite countertop. You see all sorts of minerals and stuff as part of the granite countertop. If you have Chex Mix, as simple as Chex Mix, you can pick out, the different Chex. You can pick out the pretzels. You can pick out those little cracker things that are the best, hands down. So again, here's a few examples of some heterogeneous mixtures. Oil and water is also another one, because even if you shake it and shake it and shake it, they're still going to separate. Okay, the second thing, so taking a look again at the same chart, that can kind of ask ourselves, what if we say yes? And say, is it uniform throughout? And we say yes. Well, let's see what our options are. And the matter then would be homogeneous. It's going to look the same throughout. For example, a homogeneous solution would be like, every morning I like to put creamer in my coffee, and I'm going to stir it up, and I'm going to get that really pretty caramely coffee color, and it's going to be homogeneous because it's going to look that way throughout because I stirred it up. So that leads us then to another question. Can it be separated by physical means? Can I get in there and literally pick something apart? Can I get in there and boil water off the top of it? Can I get in there and filter something out? Like maybe filter out, take sand apart from water. So if that's the case, then it's a homogeneous mixture or solution if I can do any of those things. Homogeneous mixtures, they look to be the same throughout, just like I said with my coffee example. They are well mixed, so it looks like it's not a mixture. And the particles that make up the mixture are very small, and it's not easily recognizable. It's hard to tell. And so examples of homogeneous mixtures like milk and toothpaste and mayonnaise, they're homogeneous mixtures. And they're also colloids. And I'm not sure if you've ever heard the term colloids, which is a mixture, but milk is a prime example of a colloid. But in a colloid, what happens, the particles are mixed together, but they're not dissolved. So they look like all throughout. They're kind of like permanently suspended, and they just hang out. And honestly, if you take a dark room and you take a flashlight and you shine light at a glass of milk, like obviously a transparent glass of milk, then you'll see like particles throughout. Because what happens, it doesn't separate. it just hangs out there and it just stays there. And it's kind of like humidity, for example. When we have humidity in our atmosphere, it's kind of like the fog is an example of the colloid. When the humidity is just hanging out in the atmosphere, it's not necessarily settling, it's not reaching the clouds, it's just hanging out in the atmosphere. Fog is a prime example of a colloid as well. It will not separate upon standing, and a lot of times it allows to scatter light. So that's another reason why, like, you take a flashlight and shine it at milk, it can scatter the light. Solutions is a type of homogeneous mixture when one substance dissolves in another. And dissolves, remember, it goes to the party, mingles at the party, and leaves the party together when something is dissolved. It is the best mix of all mixtures. Sometimes you can't tell that it is a solution just by looking at it. A solution has a substance that does the dissolving and gets dissolved. And this is just the first time you'll hear this, but we will do this again. But the substance that gets dissolved is the solute, and the substance that does the dissolving is the solvent. And ocean water is a solution, just like we've talked about with density. The universal solvent is water because water can dissolve most things. And water as a solvent, of course, like body fluids also are water solutions. We've talked about that also with our blood being mainly water. Most solvents are water. So here's some types of solutions, and sometimes you can actually like dissolve gas into gas, so you're mixing air. You can obviously dissolve gas into liquid, so when you're making like, soda water, so if you have one of those like soda streams, that works out really good. Obviously, you can dissolve a solid into a liquid, and the only way really to dissolve a solid into a solid is by melting down, and those are called alloys. So that's another little vocab word. When you melt and you mix basically metals that are melted and mixed. Air is a solution, and it's oxygen and nitrogen, and there's a little argon, a little carbon dioxide, but mostly nitrogen, and nitrogen's about 78%, and then oxygen's about 20% of our atmosphere. Alloys, here's some examples. So stainless steel is an alloy, and it's of iron and chromium, and brass. So your brass instruments is an alloy of copper and zinc. And finally, if you cannot separate it by physical means, then it's a pure substance. So it's going to be an element or a compound. And so if you just have the element, elements are the simplest pure substance, cannot be changed into anything simpler by heating or adding any chemicals or anything. Smallest part of an element's an atom, which you probably know this already, and there are more than 100 known elements in the universe. Listed on the periodic table of elements, there's 118 that we know now, and there'll probably be more in your lifetime. Elements are made of atoms. Atoms are the same element, and they're alike. And atoms of different elements obviously do not make up the same element. So if you have copper atoms and iron atoms together, you're going to have two different elements together. Of course, in 1813, we'll talk more about like the beginning of the periodic table. So this is just basic part of the periodic table. And then compounds are also pure substances. They are made from more than one element, sometimes two, sometimes three, sometimes even more. Water is a compound, what you see right here. We call it a molecule because it's a covalent compound, which we will learn this year. And we can break it down into hydrogen and oxygen. So, you guys, overall, I just want you to jot down some notes of what you don't know, which you probably know a lot of this, and just take some time to work on your packet to answer some questions that you might not have thought about for a while. All right, take care.